Hi guys, today we'll take up a new question in the area of intercept calculation and also calculation of the position line or orientation of the position line. Today we'll be using Sun as an example of a celestial body. You can find the links to the previous examples in the description section below. My suggestion would be for you to watch all the videos and practice those questions together with me when you watch those videos, so you get a good understanding of how to solve these questions when you face them in the exam. So let's get started with today's example. Today's example is example number 3 for Sun as a celestial body. The question says it's about 7:46 ship's time, or in some questions you might read it as zone time or ZT. The date is 5th of October on the ship. So on the ship it's 5th of October and that local time on the ship is 7:46. The ship is in DR position, 42 degrees south and 64 degrees 30 minutes east. DR, as you know, stands for dead reckoning. The sextant altitude of the sun's lower limb. Now these are some of the things you have to highlight in the question, that it's sun's lower limb. The sextant altitude was 27 degrees 35.5 minutes. The index error was nil, so no issues with that, and the height of eye was about 15.2 meters. The chronometer, which was 26 minutes 5 seconds slow, so the error of the chronometer is 26 minutes 5 seconds slow, and it showed 3 hours 20 minutes 14 seconds. You have to calculate the intercept. You have to calculate the intercept as well as the orientation or the direction of the position line. Position line is also called PL. Alright, so let's get started. So before we start off with solving the question, you first have to solve the ambiguity of the chronometer time. So the chronometer time given to you in the question is 3 hours 20 minutes 14 seconds. That could mean 3 hours in the morning or 3 in the afternoon. Because like I've said before numerous times, that the chronometer is like an analog watch. If you don't know what's going on outside, if you don't know the time of the day, looking at the watch alone, looking at the chronometer alone, you will not be able to decipher whether it's 3 in the morning or 3 in the afternoon at GMT. So what we do is we write down the chronometer time as given to us in the question, and then we write down the second possibility of it by adding 12 hours. So we add exactly 12 hours, 0 minutes and 0 seconds, and we get two possibilities of the chronometer time and the resulting GMT. So the chronometer time here could be 3 hours 20 minutes 14 seconds or 15 hours 20 minutes and 14 seconds. You will add the error now. The error is slow, so you will add the error. If the error is fast, you would subtract the error. Because the error is slow, you would add the error. In both the cases, it's the same amount. Now normally the chronometer error is not that large, 26 minutes and 5 seconds, but this is only for the purpose of the question here. So in reality, we don't allow the error to go up to such a large amount, all right, or large number rather. So when you add the error to the chronometer time, you get the GMT. So you have again two possibilities of GMT, so you have to find out what is the correct GMT for you to use for the rest of the question. So to solve that ambiguity, you will apply your zone correction. Now what is your zone correction? Zone is obtained from your longitude in time, or LIT. LIT stands for longitude in time, which you obtain by dividing the longitude given to you in the question by 15. So when I divide longitude by 15, I get 64 degrees 30 minutes divided by 15 as 4 hours 18 minutes. Now again, I have explained all this in my previous videos, but I'll quickly explain this to you again, that if all countries kept time as per the longitude, this is the time they would be keeping with respect to the GMT. But that is not a practical way of doing business in the world. So that's why every country has a particular zone. Some large countries like US and Australia, they have different time zones within the same country, but then again it's a whole number. It's not in hours and minutes, except for of course countries like India, which are 5.5 hours ahead of GMT. But here we have 4 hours 18 minutes. So if your ship is within the longitude 64 degrees 30 minutes, you would not be keeping a difference of 4 hours 18 minutes, but you would be rounding it off to the nearest whole number, which in this case is 4 hours. Anytime it would have been more than 30 minutes, you would have rounded it off to the next hour. Because you are in east longitude, your longitude is east, your ship will be ahead of GMT. The time on your ship is ahead of GMT. GMT is behind you because you are in east longitude. So you would add the zone correction to the GMT and you get 2 zone times or 2 ships time. Alright, zone time is also called ship's time. So when you get two zone times or two ship's time, you look for the hint in the question. The hint in the question was that it is 7:46 ship's time on 5th of October. So then you know that the second scenario is not the correct scenario. The first scenario is the correct scenario. It's 5th of October on your ship at 7:46. If you have just added 4 hours to the GMT, so on GMT as well, at GMT as well rather, it should also be 5th of October. So your correct GMT time and date would be 5th of October 3:46:19. This is the time that you will be using for the rest of the question. So you have to be careful with this because sometimes students in a rush start solving the rest of the question with the zone time. Do not do so. Use the GMT time. So highlight it in the question itself or highlight it when you solve it so that you know that this is the time you have to use. Alright, so I'll proceed further. So using that time, you can obtain the declination of the sun, you can obtain the GHA, and I'll show you how to do that. Let's get started. We'll have to go into the nautical almanac for 5th of October 3:46:19. So I go into the nautical almanac and I have the 5th of October here. You can see on the top it's 5th of October 2004 and the sun is right here, right? I need it for 5th of October, which is the last date in the series here, and I need it for GMT 3 hours. So extreme left hand corner you can see the GMT time written to you, so that's 3 hours, and the GMT for 3 hours is the GHA for 3 hours is 1 2 3 4 2 to 7:54. The declination of the sun is 4 degrees 49.6 minutes south. So at this point, if you want, you can pause the video and watch it slowly. I'm just trying to show you all the values at one go so that I don't have to go backwards and forwards from the calculation because it might be a bit distracting for all of you. So just pause the video and slowly find out where I've got the values from. So you can see the declination is 4 degrees 49.6 minutes south, but as you go from 3 hours to 4 hours, the declination is increasing. So from 49.6 it's becoming 50.6. So the declination correction will be applying for the minutes and the second section would be addition, will be adding it. All right, but to find the declination correction we have to highlight the D value here. The D value is 1, but we'll be using the D value to go into the increments page and finding out the correction value. All right, so what we'll be doing is we'll be going into the increments page. So we'll be going into the increments page for watt, minute and second. So let me go back. So for 46 minutes and 19 seconds. So you can see here I have written down the declination, I have written down the GHA, I have written down the D value here. So I have to find out the increment value and the declination correction value. Alright, so for 46 minutes and 19 seconds. So when I go back into 46 minutes and 19 seconds, this is my increments page for 46 minutes and 19 seconds. So you can see here this is 46 minutes, this is sun and planets are under the same column, and 19 seconds is here. So my increment would be 1134.8. My D correction value, so you can see here the V or D values are under this column and the correction value are under this column here. So your D value was 1. So the correction value corresponding to the D value is 0.8. So that's the correction I'll be using. So when I go back into the calculation, you can see that that's the declination I have used. The increment 11 degrees 35 minutes. The declination is 0.8, and you will be adding these values. So declination was increasing going from 3 hours to 4 hours, so it will be adding it. And then of course we have the GHA and we'll be adding the increment here. Increment is always added. So once you add it, you will get 239.29. Then you have longitude east given to you in the question. So whenever it's longitude east, GHA is least. That means you add longitude to it. If it was west longitude, you would be subtracting the west longitude from it. Alright, so you'll be subtracting the west longitude if it's west longitude. If it's east longitude, you always add it because the rule of thumb is longitude east, GHA is the least. So GHA is less than LHA, and if longitude is west, GHA is the best. GHA would be more than LHA. Alright, so I have a small doubt here. I'll just go back and see 46 minutes and 19 seconds. So you can see my increment was 11 degrees 34.8, not 35. So I wonder why I've taken 1135. So I should be using 1134.8 here. So because this 46 minutes and 19 seconds is the time. So my apologies for that. So actually this should not be 35. You should not round it off. You should be writing it as 34.8. So we'll write 34.8 here, and we'll write 28.8 here. So 88, and then 28 plus 30 is 58.8. So we will write 58.8. So I don't want you to get confused as to why I took. Alright, so that's the correct way to go about it. That's right. Alright, so I don't want you to get confused as to why I took 35, not 34.8. It should be 34.8. It should be the exact value. So not much difference here anyway. So once we get the LHA by adding the longitude east, we will name it. In this case, I have named it east. Why? Because if LHA is between 0 to 180, it is west. If it is greater than 180 to 360, it is east. So that's why, because this is greater than 180 and between 360, I have named my LHA east. Then we simply put in formula cos CZD. CZD stands for calculated zenith distance. Calculated zenith distance equals cos of lat multiplied by cos of dec multiplied by the cos of the LHA. Then addition or subtraction, sine of lat, sine of dec. Now why I said addition or subtraction? Because it will be depending on whether the lat and dec are same names or different names. So in this case, latitude and declination are the same names, because the latitude is also south. The latitude is 42 degrees south and the declination is 4 degrees 50.4 minutes south. So because they are the same names, I will be adding it. So find out the values of cos lat, cos dec and cos LHA. I have gone up to 5 decimal places. You can go more if you have the time in the exam. Otherwise stick to 5 decimal places. This will give you reasonable accuracy. Match the values with the one that I have written here. Alright, otherwise check your values in the calculator carefully. Then add the two values. What you get is cos of CZD equals 0.47036. Take cos to the other side, it becomes cos inverse, and CZD should be equal to 61 degrees 56.5 minutes. Alright, so calculated zenith distance has been calculated. Then we find out the true zenith distance. So we use the sextant altitude given to us in the question as 27 degrees 35.5 minutes. The index error is nil, so it's insignificant. I get my observed altitude as the same as sextant altitude. Then I find out my height of eye or my dip correction for the height of eye of 15.2 meters. So I will be going into the nautical almanac again. For 15.2 meters, I have to go into the height of eye tables. So this is my height of eye table. You can see here is the dip or the height of eye correction. Height of eye is here, the correction value is in the middle. This column is in the meters column, this is the feet column. So we have 15.2 meters, which will lie somewhere here between 15.1 and 15.5. No interpolation required. Straight away take off the value of the height of eye and go back and write it down in the calculation as minus 6.9. So that's what I've written here. Once you subtract the height of eye, you get your apparent altitude, 27 degrees 28.6. So you will be using the 27 degrees 28.6 value and going into the total correction column for sun. Now before you go into that column, you have to make a note of a couple of things. Firstly, what month is it? It's October. And the second thing is whether it's sun's lower limb or upper limb. So it's sun's lower limb, and I told you in the question itself that highlight it because this is important information. So it's October and it's lower limb, and the value of the apparent altitude is 27 degrees 28.6. So when I go back into the same table, you can see the total correction for the sun is given here. For October to March, it's here, lower limb is here, and the apparent altitude value is here. So apparent altitude value was 27 degrees 28.6, which should be somewhere, not there, but here, right, between 2634 and 2750. So the correction is plus 14.4. No interpolation required. So straight away take this value. put it here as 14.4, and remember all these corrections are in the minutes side, so don't add it onto the seconds the degrees side. So when we add the minutes, you get 2743 as true altitude. Then to get the true zenith distance, simply subtract it from 90 degrees. Alright, take the smaller value and subtract it from the larger value. Do not write negative. Zenith distance cannot be in negative. Alright, so it's 90 minus true altitude, but we write it in this way so that you understand that this steps comes after the true altitude. So you subtract 27 degrees 43 minutes from 90 degrees and you get your TZD or true zenith distance, which is 62 degrees 17 minutes in this case. Then you write down your calculated zenith distance below the true zenith distance. The difference between the two should give you your intercept, which in this case is 20.5 minutes. 20.5 minutes, and then you have to name it whether it's towards or away. So how do you do that? You use the rule of thumb here. True, tiny, towards. What does that mean? That means if true is tiny, if true is less than CZD, then you will be towards. If true is more than CZD, it will be away. In this case, your true is more than CZD. Your true zenith distance is more than calculated zenith distance. So true is not tiny here. True is larger than calculated zenith distance. So your naming would be away. Alright, so once you got your intercept, you just have to find the orientation of your position line. To do that, find out the components of A. A equals tan lat by tan LHA. Put in the values of latitude and LHA straight off. Ignore any negative sign that you get in the calculator. Alright, ignore the negative sign. Simply put in the value. I have stuck to 2 decimal places. You can go up to more decimal places if you have the time in the exam. Although you ignore any negative sign, you have to name A. So I have named it north. Why? Because A is always named opposite to latitude, unless your LHA is between 90 and 270. In this case, your LHA is 303, which is not between 90 and 270, so you will name it opposite to latitude. Your latitude is south, so you have named it north. Then you find out B by dividing tan of declination by sine of LHA. Again, simply put in the values in the calculator. Again, ignore any negative sign that you get, but name your B. When you name your B, you name it same as declination. Alright, so your B is south, so you will name it south. So once you got your A and B, write down the values here, A and B. Now depending on whether they are same names, you will be adding it. When we say same names means if both are north, if both are south or both are north, you will be adding it. But if they are different names, one is south and the other is north, you will subtract it. Subtract the smaller value from the larger value in this case because one is north, the other is south, and you get 0.51. You will name C north because you always retain the name of the larger. What does that mean? So out of A and B, which value is larger? A is larger. And A is named north, so you will name the C north as well. Alright, once you got C, put it in the formula tan azimuth equals 1 divided by C times cos of latitude. Put in the value of C and cos of latitude, so you get 1 divided by C times cos of latitude. Solve the denominator first. In the calculator, do not put 1 divided by C times cos of latitude. You will get the wrong answer. Solve the denominator first and then divide 1 by it. And then you get tan of azimuth equals 2.63852. Take tan to the other side, you get tan inverse of the same value, and the answer you get is 69.2 degrees. But in this case here, you will name it northeast. Why? East comes from name of LHA. Your LHA was named east above. Remember? We named LHA east because LHA was between 0 to, it was greater than 180 and between 360. So we named it east. So that's why you will name it east. North comes from name of C. So you named your C north. So you will name your azimuth here north as well. So north 69.2 degrees east. What is north 69.2 degrees east? Is the same as this is north, this is east, this is 0, 0, 0. Going from north to east 69.2 degrees is same as 069.2 degrees. So your bearing is 069.2 degrees. At this point, let me tell you that for practical purposes, we actually round it off to a whole number. So in this case, I would be actually rounding it off to 69 degrees because if you have to plot it on the ship or plot it on the chart, then you cannot plot 69.2 degrees. You can plot either 69 or 70. To the maximum, you can plot about 69.5 degrees, but not 69.2. So depends on what you have been told, but both the answers will be correct according to me. So you can name it either 69 or 69.2. So once you got your true bearing as 69.2 degrees, to find the orientation of the position line, just add 90 degrees to it. 90 plus 69.2 is 159.2, or subtract 90 degrees from it. How do you subtract 90 degrees? So 069.2 plus 360 degrees. Make it larger than 90 degree by adding 360 and then subtract 90 degrees from it. You will get 339 degrees. 339.2 degrees. Alright, in this case, of course. So 339.2 degrees is what you will get. So your orientation of the position line is 159.2 to 339.2 degrees. So what does that mean? That means is when you are plotting, and you will be plotting, is it towards or away? It's away. So what you will be doing is you will be going not towards 069.2. If this is north and this is east, this is west, and sorry, this is south, this is not west, this is south, this is west. So instead of going towards 69.2, you will be going away from 69.2, reciprocal course. This is means going away. Now this distance would be the intercept distance. This is 20.5 minutes, what we have calculated. And when you draw a line perpendicular to this line here, this line is in the orientation of 159.2 and 339.2. That is what it means. This is PL, or position line. Alright, this distance is the intercept distance. So I have discussed all this in my videos on staggered observations. So make sure you watch those videos as well, because you will learn how to plot these calculations and plot these observations. Otherwise, if you have any questions regarding this topic, feel free to write it in the comments section and I'll try my best to